as engineers, we need to have a really good understanding of stress and strain, because if you're designing pretty much any device, machine or structure, you need to have a good understanding of stress, because if you design it so it becomes overstressed, it could fail, and similarly, if it's too lightly stressed, it might be too heavy for its intended purpose. So that's what we're going to look at this lesson, is calculating stress and strain. So, stress and strain. And you've got a picture there of a bolt before and after a stress test where it's actually failed the test. Now, the aim of the lesson today is for you to be able to perform stress and strain calculations and also cover calculations for Young's modulus. Let's get started. So, examples of stress. Now, stress is defined as force over an area. And in engineering, we tend to think of stress as a tensile or pulling stress. A tensile or pulling stress. You can get compressive stresses as well, but normally in engineering we think of tensile stresses. And obviously a component that fails its maximum tensile stress will fail in a catastrophic manner with catastrophic results. I've got an example here on the right hand side of a piston and the connecting rod here, which connects the piston to the crankshaft, is subjected to huge tensile and compressive loads every time the piston goes up and down. And that's a very important part of the design, is getting this cross section here right so it can withstand the enormous tensile stresses it will have to withstand. Another example of tensile stresses, I've got a diagram of a suspension bridge here, and the green shows the parts that are in compression, which are loaded in compression, and the red parts are the main tie rods here, or the cables here, and the main cable across the top of the bridge as well. All of those are in tension, pure tension. Now, some more examples of stress. Now, you may not think at first sight that a beam like this one in a building is subject to any tensile stress, but in fact it is, because when a beam like that is put under load, you get a tensile stress at the bottom of the beam and a compressive stress at the top. And so therefore tensile stresses have a direct connection to things like beams. Another good example is this picture here. This is a picture of an RB, a Rolls-Royce Trent 1000 engine. These fan blades on the front of the engine are subjected to huge stresses. Part of it from the actual rotation of the engine. This rotates at around about 40 times per second. So there's huge centrifugal forces trying to pull the blades away from the shaft. And also there's a huge bending load as well for the colossal amount of air that is pushed through the engine, particularly on takeoff. So these blades are subjected to enormous stresses, and it probably takes several thousand man-years of engineers' time to design them, to get them to work properly and also to be light as well. But they're still looking all the time at stress and strain. A little bit more about stress testing. Now, stress testing is quite a big little industry because new alloys are being developed all the time for use in things like aircraft engines and racing car engines and so on as well. There's quite a big industry actually testing these. And in the top right up here, we've got some tensile test specimens. These are then mounted into a tensile test machine, which is shown below, and pulled to see how strong they are and work out the stresses. You can also do tensile tests on plastic specimens as well. And if you select either Unit 25 or 26 of this course next year, then you will actually go ahead and actually carry out some of the tensile tests on different materials. So, the definition of stress, as I said earlier, is the force per unit, or the load per unit area. So it's a fairly straightforward equation. Stress equals force over area. Now the units for stress are newtons per metre squared, because we've got a force in newtons divided by an area in metres squared. And so the unit for stress is newtons per metre squared, which I prefer to use because it's quite explicit, force over area. But the one that's used quite widely is the Pascal. So 1 Pascal equals 1 Newton per metre squared. And that's the one that's preferred by the exam board. So that's the one I use for these examples. Now you can see here, you can obviously double the stress by doubling the force, but you can also double the stress by halving the area that the force actually acts on. Now the good news for you is all the formulas you'll need for stress and strain calculations are included on the formula sheet, and we'll look at that a little bit later on to make sure you're comfortable with that. So here's a sample calculation. We've got what is the stress on a rectangular strip, 0.1 metres by 0.005 metres when subjected to a load of 200 newtons. So the first thing you need to work out, remember stress is force over area. Let's work out the area, and the area of the strip is 0.01 times 0.005, giving you 5 times 10 to the 5 metres squared. Stress we know is force over area. We've got the force, we now know the area, and you can just calculate 200 divided by 5 times 10 to the minus 5 gives you a stress of 4 times 10 to the 6 pascals, or newtons per metre squared. Now going on to meters or millimetres. Normally you need to calculate in metres. So things like, as I say, pascals are newtons per metre squared. But often you're given a size in millimetres and it makes sense to convert it to metres straight away. Now, hopefully you'll remember that 1 millimetre is 1,000th of a metre. So 8 millimetres divided by 1,000 gives you 0.008 metres. So 8 millimetres equals 0.008 metres. So therefore an area of 8 millimetres by 20 millimetres would be 8 times, 0.008 times 0.020 gives you 0.00016 metres squared. Or you can represent that by 1.6 times 10 to the minus 4 metres squared. Either of those are good in an exam. Obviously you don't want to go around putting too many zeros in there. It looks a bit messy. It takes time to write it out. It's quite easy sometimes to forget one of them. But that's how you can represent that. And the same applies to the radius or the diameter of a circle as well. You may well be given that in millimetres. You need to convert that into metres squared. And you may remember that the area of a circle is pi r squared. Now this isn't actually on the formula sheet. You do have to remember that. So let's go into a practice question. So here's a practice question for you. And the steel bolt, 15 millimetres in diameter, is subjected to a force of 22 kilonewtons. Calculate the stress on the bolt. So pause now. The answer you should have got for stress is 12.4 times 10 to the power of 6 pascals. If you got that, well done. If not, we'll go through it. Okay, so we know that stress is force over area. We don't actually know the area yet, so that we need to calculate that first of all. So the area is 15 millimetres in diameter. We know for the area of a circle, the formula is pi r squared. Now, we've got the diameter there. We need to convert it to metres as well. So we know that 15 millimetres in diameter equals 7.5 millimetres radius. And to convert that to metres, we just jump the decimal point along a bit. So it's 7.5. Go 1, 2, 3. to divide it by 1,000. So 7.5 millimetres is 0.0075 metres. So we put that into our formula here. Pi times 0.0075 squared comes to 1.77 times 10 to the power minus 4 metres squared. Okay, and then all we need to do is to put it into our stress equation, and that comes to 22 times 10 to the power of 3 divided by 1.77 times 10 to the power of minus 4, and that comes to 12.4 gigapascals. So remember, lay it out nice and clearly and put your units in as well. Okay, so we know what stress is now. So what's strain? Now, strain is the amount of material stretches when under stress. That's the definition of strain, the amount of material stretches when under stress. Now, I've got a little diagram just there of a metal bar with its original length here. It's then subject to a stress, and then there's a change in length. This is the change in length we're actually interested in. So the formula for strain, and again this is on the formula sheet, we'll look at that in a minute, is the change in length over the original length. Now it's very, very important to get this bit right. It's the change in length, that's this little bit here, not the new length. It's the change in length divided by the original length. Now you may think about the units for strain. Now because you've got length divided by length, strain is actually a ratio. It doesn't actually have any units. So if it's millimetres change in length divided by the original length in millimetres, it doesn't matter. They cancel out. So strain is just a ratio. And the other thing to be aware of is that for metals, the strain is normally well under 1%. It's usually a very small number. So if you have a steel bar or a steel bolt and you can stress it almost to breaking point, the strain, the change in length, is very, very small. It's quite hard to measure. It's very important to measure it accurately, but it's not something you can see with the naked eye. Obviously things like plastics and so on give a lot more easily, so you can see strain in plastics. So let's go into a calculation using this. So we've got a situation here. What's the strain when a bar 0.28 metres in length is stretched to 0.282 metres? So we've got our strain equation there, change in length divided by the original length. So we need to find the difference between 0.282 and 0.28, which is 0.002 divided by 0.28, gives you a strain in this case of 0.00714. And as I say, normally the strain numbers are pretty small. And if you're asked to calculate a strain in a piece of steel or something and it comes out at 10%, you probably drop your power of 10 somewhere or something like that. Okay, so a short Greek diversion now. We're going to quickly look at the Greek alphabet, and this is the reason why. Now, if you look in the formula sheet, you'll see the formula for stress and strain, and you'll see it's got this little squiggle here and another one here, one for stress and one for strain. Now, the reason we use Greek symbols is because very quickly mathematicians, engineers and scientists realised that the 26 letters in the European alphabet weren't enough for all the equations that there were in these subjects, and therefore they borrowed some letters from the Greek alphabet to give us more variety. And so you should by now already be familiar with, for example, pi, because pi represents the number 3.142. Just a lot more convenient to write down pi all the time. And you should also hopefully remember from your physics days the 3 different types of radiation: alpha, beta and gamma. Again, Greek letters to represent something. Now these ones we've got here are sigma for stress, that's this little symbol here, sigma, and then this curly E is called epsilon, and that's used for strain. Now the thing that gives students the heebie-jeebies is this funny little triangle in front of the L. Now that actually simply means the difference or change in length. So that means difference or change in length divided by the length. Just turn the music off there. And let's look at the next practice question. A bolt from the previous example is 200 mm long, and when subjected to a force it extends by 200 to 200.8 millimeters, and all you've got to do is to calculate the strain on the bolt. So have a go at the question, and when I tell you to pause the video, and then I'll give you the answer. So pause the video now. Okay, the answer you should have got is 0.004 or 4 times 10 to the minus 3. If you got that, well done. Jump on to the next section. If not, we'll go through it.
Okay, so here's question 2. The bolt from the previous example is 200 millimeters long, and when subjected to a force it extends to 200.8 millimeters. And all you've got to do is to calculate the strain on the bolt. Strain is change in length over original length. So in this case, the strain is just the 0.8 millimeters it's got longer. That's the change in length. Okay, now because strain is length divided by length, we don't need to convert this to meters. We can actually leave it at millimeters. So I'm going to do it that way. So the change in length is 0.8 millimeters, and the original length is 200. So divide one by the other, and that comes out at 0.004. And they said that's a ratio, it's not actually a number, and the result will be just the same. If you did convert it to meters, the number's exactly the same because it's a unitless number.
So now I want to look at unit prefixes. Now you do use these quite a lot in engineering, and again some of you will be familiar, or you should be familiar with some of them already. Now the one you're probably most familiar with is kilo, and that's an abbreviation for 1,000 of something, because the metric system scales things in thousands. So a kilometre is 1,000 metres, a kilogram is 1,000 grams, and so the true number is 1,000, and as a power of 10 it's times 10 to the power of 3. Another one you've probably come across is mega, which is 10 to the power of 6, or the true number a million. So a mega ohm, for example, 5 mega ohms is 5 million ohms for a resistor. The other one we're going to look at is giga, which is 10 to the power of 9. So that's 1,000 million. Another one you're probably familiar with is going the other way, going smaller, where milli is 1,000th of something, and that is 10 to the minus 3, or 0.001. So again, you're probably familiar with millimetres, 1,000th of a metre. And also the other one that you come across quite frequently in engineering is micro, which is 10 to the minus 6, or 0.000001. And you've got a couple of examples here. 6,400 newtons could also be represented as 6.4 times 10 to the power of 3 newtons, or 6.4 kilonewtons. And similarly, a value of current, for example, of 0.000006 amps is much more conveniently represented as 6 times 10 to the minus 6 amps, or simply 6 microamps. Just quicker and easier to do things that way. So we're going to look at some examples where we're going to need some of those values. Now, we've looked at stress and strain so far. Now we want to talk about Young's modulus. And the formula for Young's modulus is sigma over epsilon, which we now know is stress over strain. Now the Young's modulus is calculated for different materials. It's also known as the modulus of elasticity. So it's got two names, which can be a little bit confusing, but Young's modulus is the one that the exam board is using, so we'll stick with Young's modulus. And basically, this is a property of a material, and all materials have a Young's modulus, and it's an indication really of how stiff the material is, how much it deforms under a certain load. Now the units for Young's modulus, normally they're very big numbers because the stresses, as we know, are very large and the strains are normally very small, so you do get some seriously big numbers. And these are some values here for typical materials you're going to come across in engineering. The Young's modulus for steel is around about 200 gigapascals. That's 200,000 million newtons per metre squared. Aluminium comes in at 70 gigapascals. Rubber, which is obviously a much softer material, comes in at a much, much lower value. And most plastics are 2 to 4 gigapascals. If you need the number, you will be given it to you in an exam. So here's another question for you to have a go at. So using the data from the previous question, calculate the Young's modulus for the bolt in question. And remember, state the units. Please get into the habit of always stating the units. So have a go at this and pause the video now. Okay, so the answer you should have got is 3.1 gigapascals. So 3.1 gigapascals for this particular material. If you got that answer, well done. You've pretty much finished the unit. You can now go on for the test questions. If not, I'll go through it.
Okay, so for question 3, we're using the data from the previous questions and we've got to calculate the Young's modulus for the bolt. And again, state the units, get into the habit of always doing that. So we know the formula for Young's modulus, we know that's stress over strain, so I'll write that out. Equals stress over strain. So we put in our value for stress, which was 12.4 times 10 to the power of 6, divided by 0.004, and that comes out to 3.1 gigapascals, or you could say 3.1 times 10 to the power of 9 pascals. Doesn't really make any difference. As long as it's clear, that's all you need to do to calculate Young's modulus.
Okay then, so we've got to the end now of the lesson on stress and strain, direct stress and strain that is, and hopefully you can see the importance of stress and strain in engineering situations. And the important thing to remember is that obviously although you're given the formulas on the formula sheet in the exam, the real important thing is to remember that stress is something you can do to a material by simply pulling it, and that's force over area, and strain is the resultant extension, how much longer it gets. So strain is the result of stress. Now, as usual, there are some more questions for you to have a look at. There are 2 sheets. I'll show you what they look like now, but you should have hard copies of those. And if you go through those, you'll find as you go into them, they get more challenging, more difficult, higher standard up towards the distinction level, and you may get a question where you've got to calculate back from a stress and a Young's modulus to calculate the diameter of a bolt or a wire to perform a particular job, and that's more typical of a distinction style question. So well done. The next lesson is on shear stress and strain.